Okay, well, welcome back, everybody. I know that was a short break. I'd like to work on using these ideas now to implement some more interesting simulations with network models. I don't know how far we'll get with this. As I mentioned before, all of the examples are distributed. They were emailed to you, and all of the slides will be available. So if you want to use these as reference materials, you've got it. This is module 4.1 for the workshop, talking about multi-scale network modeling integration. And I need to remind you that the workshop is live streamed and recorded and distributed on YouTube. So today we're going to focus on the delta notch model, and then we're going to talk about how to do steering panels, which are useful when you're going to distribute the simulations. I'll talk a little bit probably about how to add steppables using Twedit, because that was asked about before. And I probably won't have time to talk about loading SPML models from the biomodels database. I'll just mention that it's possible and refer you to the slides. As before, I want to remind you that we have these great references for antimony. These great references for antimony, Herbert's textbooks, the cheat sheet that we gave you, and the online documentation. There are lots of great textbooks that you could look at for network modeling, for ideas and approaches. The antimony syntax, again, is very simple. You put the model string together in triple quotes. You specify rate laws with names, with colons in front of them. And the syntax is something goes to something with an arrow, semicolon, rate law. You specify the values of the parameters and the initial values of your variables. That's all you have in antimony. The key ideas we're going to use are how to add a free-floating antibody model, or adding an antibody model to a cell. We'll typically be adding it from a model string rather than from a file. So the syntax will be self.add antibody model to cell. The model string equals the name of the model string. Give the model a name, because we're going to be referencing it by that. Cell equals cell, the cell we're adding it to. So again, cell here on the right might be something else like neighbor or second cell or something of that kind, any handle. And then the step size. We have the variety of options like Gillespie integration and so on that we could use, and we time-step antibody models with self.timestep SPML. Always remember that we have the Twedit's code snippets and the manuals at hand. Also remember that the Twedit code snippets often need to be edited, but you'll be pasting it as a template, and it may give you multiple options of which you can only use one at a time. And so you have to delete the extras, and you also have to replace the placeholders for names and handles with the things that you're using. I'd like to talk about delta notch patterning. This is one of the key signaling mechanisms. It's a juxtacrine signaling mechanism in early development. It shows up in almost every organ system in developing embryos, both in vertebrates and in other simpler animals like Drosophila. Here it's in the hair cells in the ear, photoreceptors in the eye, human intestinal crypts, and you can find lots of literature on delta notch. The actual delta notch pathway is pretty complicated, but the key thing that's interesting about delta notch from the point of view modeling is that it's a juxtacrine mechanism. Every cell has a delta and notch on its surface. Delta on a cell touches notch on the neighboring cell. Notch on a delta on the neighboring cell touches notch on my cell. The fundamental question is essentially the difference between the delta and notch signals. There are some cis interactions where delta and notch on the same cell cancel each other out. But the basic idea is that delta on one cell inhibits delta on the neighboring cell. Notch on one cell inhibits notch on the neighboring cells. And so you tend to get this salt and pepper pattern where you'll get a high delta cell surrounded by low delta cells in this kind of hexagonal checkerboard. And that's very typical. Lorenzo Vischini, who's on the call and helping us out for the workshop, is an experimentalist working in this area and also doing a detailed modeling of this. And I strongly encourage you to talk to Lorenzo about building more sophisticated delta notch models. The one we're going to do today is an absolute minimal model of delta notch, mainly to illustrate how these things are done. But the key thing is that activated notch inhibits delta, and activated notch here inhibits delta. That's the key feedback loop that we're going to get. This is something that's rather difficult to do if you're studying a single cell, because the key thing is actually the interactions of pairs of cells. A single cell by itself doesn't do anything interesting with delta. There's a very simple model by Collier from 1996, which simplifies the rather complex biochemical networks of delta and notch to two fundamental concepts. You're going to have the amount of activated delta inside each cell, which we'll call D, the amount of activated notch inside of each cell, which we're going to call N. We're going to say that the amount of delta depends, delta is inhibited by notch, so that the more notch we have here in the denominator, the less delta we get. Delta decays naturally. So there's a first order decay. The amount of notch we get, notch is promoted by delta on the neighboring cell. This delta is not the delta in my current cell, it's the delta on my neighbors. So this is the signal I'm receiving from my neighbors. So if I were in a single cell, this would be 0, and the model wouldn't be interesting, and notch decays itself. And so this very simple model is what we're going to caricature delta and notch with. And we're going to need some parameter values. This is called a Michaelis or a Hill constant. A is 0.01. B here, the scaling of notch is 100. The velocity of the delta reaction is 1. And the Hill exponent H, we're going to use a value of 2, which is fairly soft. Those are all things that we could play with. So if we run this model, this is actually an old simulation. It looks prettier when we run it today. The one we'll build here together is a prettier one. We'll see this patterning of delta and notch that is going to be pretty typical. You'll see a lot of fluctuation, and then depending on the situation that you built, you may get a stable pattern or you may get oscillatory patterns. So the exercise that we're going to do today is you're first going to create a space filled with cell using uniform initializer. You're going to type this string as an antibody model, and having said that you shouldn't use ODEs, we're going to be using ODEs. We could write this as a network model, but we're not going to do it today. We're going to add this model to all of our cells individually, so each cell will have its own model, because it doesn't make sense to have an average one. Then at each time step, we're going to loop over each cell, loop over that cell's neighbors, calculate the delta signal from the neighboring cells, pass that back as D average to our cell, and we're going to use the tracking fields to visualize delta and notch. If you want to see the final result, you've got it, exercise 4_1_1 delta_notch. But I hope people try building it themselves. And this is going to be a bit more of a challenge in the sense that I'm going to expect you to do some independent coding. So again, the exercise is create a simulation. Here I said 42 by 42 by 1 with a single type of cell. Use volume Here it says volume local flex. You don't need, well, you'll want volume local flex later in the exercise. So use volume local flex, contact energy, use uniform addition to fill the simulation with cells that are 7 by 7. In the Steppable, assign an initial target volume of 50, a lambda volume of 2. Use periodic boundary conditions. Then write your antimony string, load the antimony model. We're going to randomize the initial values of delta and notch in a small range between 0.9 and 1. We're going to calculate the average D from my neighbors of each cell, pass it back to our cell. And we're going to create auxiliary fields to display delta and notch for each cell. So I'm going to do this in a couple of steps. We can do this. I'd like you to try to do this on your own. I can code it also while we're doing it, but I think it's better if you try to put to work the things you thought about. The first step is create a 42 by 42 simulation domain. Again, use the wizard to do this. Volume local flex, constant contact, a uniform initializer. I think it should be relatively explanatory. So why don't people try that as an initial exercise? I'm going to start a poll, but I'm going to assume that people are going to need some time to do this. So I'm not, don't answer need more time. I'll give you a couple of minutes before I go forward. So don't say need more time until I sound like I'm about to go forward. But do by all means, if you feel that you need help, reach out and we'll put you in a breakout room to get help. So I'm mainly interested in when people are done with the exercise. So somebody already clicked need more time, but I just said don't do it. Somebody has a sense of humor.
James Farad is wondering if it might be possible to put next steps up on slides, or if the next step is the solution.
Okay. Sorry, yes, people are going different speeds here. The next step again would be to write the antimony model string corresponding to the ODEs, and I'll jump forward to show you what that is. Then load the antimony model, calculate the D, and create the auxiliary fields. So the next thing that we want to do is write the antimony string. So let's check first that we got what we have running. And see if we get the initial condition that we want. I have a typo. I type call instead of cell. So. Okay, so let me run that poll again and see how people are doing. Okay. I'll give people another minute or two to get this through. I hope people are beginning to be familiar using Wizard. I can walk you through it again if you need to. Again, CC3D project, new CC3D project, delta notch 2. I said to use 42 by 42 and periodic boundary conditions. Rectangular slab is what we want. Create a single cell type, cell. No chemical fields. Contact energy, volume, local flex, next. Finish. That gives me my template model. I have to go in and in my XML, I have to change the size of the initial simulation so that it fills the whole space. One corner is 0, 0. The other corner is 42 by 42. In my Steppables, in my start function, I have to loop over all cells. Go to CC3D Python, visit all cells. Inside of that loop, cell dot lambda, I have to spell it right, volume equals 2, cell dot target volume equals 50. And if you forget the syntax, you can go to CC3D Python, go to cell attributes, and you have all of those available to you. Okay. So the next step, I'll come back to my original one. My next step here is to type the antimony model. And so to do that, I go into the beginning of my simulation above the class definition, and I'll type model equals triple quotes and put everything together. And remember the syntax. If I want to write an ODE, I go J1 colon arrow X semicolon rate law. J1 colon arrow D semicolon D to the K gives me that. So use that as a pattern to implement these two ODEs. If somebody wants to do it as a network, that would be great. Remember, D with a bar on it is not D, it's D average. And so you probably want to call that D bar, DAVG, something like that. So let's try that. See where people go. If people get stuck, remember you have this exercise available to you. It was so you can upload it and use it as a template. Something like that should work. Did people get that? Give people a little bit longer to type that. If people have questions about how this works, please ask. I know there's a question about next steps, and I'm sorry if this is slow for some people, but we'll have some challenge exercises in a minute, but I want to make sure everybody has the basic model working. Again, if you get stuck, please load exercise 4_1_1 that was distributed to you. If people need help doing that, let me know. Okay. This is what it looked like when I typed it a little bit more formally. I used D equals 0.5 and N equals 0.5. The average is 0.4, so I guess I should correct what I typed here. In fact, we're going to overwrite those, so it's not going to matter very much. Everything else looks okay. This is one of the places where not being able to cut and paste from the chat is a little bit inconvenient, because if you could cut and paste from the chat, I could put the string in for you. The only thing I can do is give you the model upload at this point. Okay, I'm planning on moving on to the next step. I want to make sure if you need more time, is the time to click the need more time button. Looks like people are ready. So the next thing that you need to do is to load your antimony model. And you're going to be loading that into all cells. So the place to do that is in your start function when you're adding your target volume and your lambda volume to your cell. You're going to go in and you're going to add the antimony model. Here, actually, I have, as an example, add free-floating antimony model. Probably not the best choice. I've said you could add it to all cells of type A. That would work. In that case, I don't have to be inside of my loop. Or I can add it to all cells, to cells individually. I'm going to do what I suggested here, which is to add it to all cells of a given type. It's going to go outside of the loop. I'm going to go to CC3D Python, SPML solver, add antimony model to cell types. There's going to be quite a bit of syntax here, which I don't need. So I'm going to get rid of all those comments. Well, those comments could be interesting if you want to know what to do. Within this add antimony model, we're not using a model file. So we get rid of that. Our model string is whatever name we gave it here. Here we called it just model. So we'll call model string equals model. If you gave it a different name, use that. And then we need to give this model a name that we're going to use here. And I suggest using DN, capital DN for delta notch, something short. DN. I'm having a little bit of trouble with scrolling with Zoom. DN. Let me just resize a little bit so that I can get in here. I'm going to zoom out. Okay. Trying to keep it big enough that you can read, but small enough that you don't get a lot of scrolling. Step size is going to be 0.2, and we're going to get rid of all the extra stuff here. And I'm always nervous about using continuation lines in Python. It's easy to have typos. So I'm going to merge this back into a single line. And the one thing that I need here, if I'm loading by types, I need to know what my cell type name was. I need to go back to my Python here, my XML. I called my cell here just cell, which would mean here I would use as type name just cell, all caps. I could perfectly well iterate over individual cells as an option that might be a little simpler inside that loop. So I want to make sure that everybody has that. Again, if you get stuck, please load the completed example. That's what I just typed. we're going to use some random numbers. So you're going to need to load NumPy as NP. The code is shown. That's what you're seeing. This is the code you need. You'll need to load NumPy because we're going to use random numbers. So we're going to import NumPy as NP, standard Python syntax. Again, add antimony model to cell types. Model, whatever you called your model string, name of DN, cell A. In this case, I just called my cell instead of cell A, whatever you used. Step size is 0. And then while we're waiting, import NumPy as NP at the top. And I guess I can check to see if I have any syntax errors. See if I have any syntax. Looks like I'm okay. Okay, how are people doing with that? Is it okay to move to the next step? Okay, I want to initialize random values of delta and notch for each cell with a random uniform distribution between 0.9 and 1. Remember that we reference D and N, cell.sbml.dn, square bracket, quote D, close bracket, and the uniform random number syntax is np.random.uniform parenthesis min value max value. So why don't you try adding that? You can do that inside of our cell definitions. So we can say that cell.sbml.dn, if you gave it a different name, use the name that you used. D equals np.random.uniform. And you say, how do I know remember the syntax for NumPy? I don't. I would type in Google, I would say NumPy random and look up the syntax. I certainly don't remember those off the top of my head. There's a question, why did I choose between 0.9 and 1? Actually, almost any value you pick will work. Could be between 0 and 1 would work. I happen to know that 0.9 to 1 gives interesting initial conditions where it starts almost uniform and then the symmetry breaks and it takes a little bit of time. But that's exactly the kind of thing you can explore. So it would be a great idea to say, well, what happens if I change the range? If you're ahead of things, run it with that and then see what happens when you change. That's a great question. Finding parameter values is always tricky. In this case, I'm cheating a little bit because I know the answer, but you're absolutely right that you might want to use a different name. Okay. So that's what I get for here. Let's make sure people were able to do that one. And again, I strongly recommend checking your syntax as you're typing. I try to design things so that they run as you're doing it, so you don't have to do multiple steps to check. It executes, so it's okay. So again, remember the syntax: cell.spml, the name of your model as loaded, the name of the variable, and then this NumPy random number generator. If you have some other random number generator you like, random.random or NumPy random .random or Gaussian, you can use it. The principle is that you want the numbers to be a little bit different in each cell. How you get that is up to you. So there's the syntax. And now I'd ask you to add the time step of the model, and that goes in the step function. If I don't remember the syntax, I encourage you to use the Twedit code snippets, CC3D Python, SBML solver, time step SBML model. That will do that. And let me check that I didn't break anything. Again, open player. See if it does. Okay. Next step. This is the most challenging step. I want you to now, in the step function, loop over all my cells, read the delta level of my neighbors and average it, because that D average has to be passed to my model from my neighbors. The average comes from my neighbors. And this is the interconnection between the cells. This is the critical thing in this model. And so what I'd like people to do is loop over. We already have a loop over all cells, so we can use that. Use the iterators. Remember CC3D Python visit, cell neighbors. You'll have to create a placeholder to put your averages for D. You'll have to do a check if neighbor, and the iterator over neighbors will do that for you. So that's a good reason to use that. Sum the value of D, keep track of the number of neighbors, normalize by the number of neighbors, and then pass it back the way you did it here, except for D average. If you're ahead, you can make this game a little bit more interesting by keeping track of the contact area and weighting the signal from each cell by the contact area with that cell. So if you want to do a little bit of an extension, a challenge problem, do it that way. In this case, even if two cells are touching each other, if they're touching a lot or a little, the signal is the same. In reality, if you had a large contact area, that would be more important than a small contact area. And so you can spend a few minutes thinking about how to implement that. This is going to take a little bit longer, so I'll give people time to think about it. I'll do it out for myself while I'm in it. For cell and self.cell list. And now I want to iterate over my cell neighbors. And you can probably come up with a fancier, more Pythonic way of doing the averages. If you're sophisticated, I'm going to do something very basic. I'm going to say the average equals 0.0. Number of neighbors equals 0. This is going to be where I'm going to accumulate the average value. This is going to be the number of neighbors. I iterate over my neighbors. If neighbor, because if I'm next to medium, I don't want to count it. If neighbor, then I want to get the value of D from the neighbor. The value of D from the neighbor, I know my value of D is here. But instead of referencing it for my cell, I now have to reference it for my neighbor. And I want to add that to D average. Okay. And if I do this, I'm counting how many neighbors I have. So my neighbor goes up by 1. Again, you could do this by creating lists and using NumPy averaging functions too. Be a little more elegant. I'm going to do it in the simplest possible way. Okay, once I've done my loop, I'd better check if I had any neighbors, because if there are no neighbors, I get a divide by 0 error. If there are neighbors, I'm going to set cell. I have it actually already, don't I? Cell.sbmldn. Now it's the average is the variable I want, and that's going to be DAVG divided by NN. So that's going to be the code. Again, you might have more elegant ways of doing it. And while you're working on that, I'm going to check to see if I made a syntax error. Certainly possible I did. Yeah. Oh, could not find neighbor tracker plugin. One of the things in CompuCell is that when we created this model, I should have thought that I was going to use neighbors, and I didn't do it. So I have to go to my XML, and I have to add the neighbor tracker plugin. You might wonder why, if it is able to give me an error for not having it, it couldn't just add it on its own. We don't use the CC3D ML very much, but here we'll go into the XML, CC3D ML plugins. And if I look in my plugin list, down here is neighbor tracker. So I add neighbor tracker. So you may have to do that. In old versions of CompuCell, neighbor tracker was loaded by default. So one of the things that I hope people will begin to do, and one of the reasons I'm doing this with you, is that I want you to see how, when you make the mistakes that you inevitably make when you're doing this kind of coding, that you learn how to fix them, how to diagnose them and to fix them. Again, we added the plugin neighbor tracker. It doesn't matter where it goes. You could type that by hand, or again, go in CC3D ML plugins, neighbor track. The one thing I said, it doesn't matter where it goes. Don't put it inside of another plugin specification. If I place neighbor tracker here inside of the POTS block or inside of the contact energy block, it'll generate it. Okay. Show the code again. Let me see if that fixed my problem. This time it works. Okay, how are people doing? Again, if people are ahead of the game, try keeping track of contact area and weighting their signal by the contact areas, which is more realistic. Okay, I'm going to move forward. Here's our code. What I wrote was pretty close to what I have here. And now the next step is one that we've talked about before, which is creating tracking fields. And your goal here is to be able to display the values of N and D. And you're going to have to do two things. You're going to have to create a tracking field. You could call one delta and one notch. And you have to remember where that goes. That goes in the init function here. And it's a little bit easy to put it in between the init and the steppable base. It has to go in the init after the steppable base. That will throw a strange error if you do it in the wrong place. And that's a little bit of a trap for people. So you need to paste in the tracking field here, and then you are going to have to copy the value from the SBML dictionary to the cell dictionary so that it's displayed. Do the same thing for N and for D. So I come here in my just after my steppable, CC3D Python, extra fields automatic tracking, track scalar cell attribute. Give the name of the field, my display name. Let's call it notch. Doesn't matter what the name is, something that's meaningful. The attribute name, I'm just going to call it N, capital N for notch. I think that the tracking fields are actually probably the single nicest thing that CompuCell has.
So, question?
Yes.
Yeah, since we have a species defined as N, would it interfere with the attribute name for the tracking field?
Good question. If you're nervous about that, you should definitely give these different names. A dictionary key and a variable are independent of each other. And we have a tendency to do things like cell equals cell, where cell is a handle on one side and cell is a variable on the other. You definitely could give the attribute name something else like N1 and D1 here. You just have to be sure that you're consistent. This is a key, it's a dictionary key. Attribute name is a dictionary key. And you can have a dictionary key be the same name as a variable. But you're right that that could cause confusion. I'm going to keep it as N and D because that's how my code example has it. But you're right that if you should be, as good coding practice, you should probably have different names so that you don't get things confused. Great question. So I add my tracking fields here, and then in my step function, I'm going to have to copy the values of my cell SBML. Here's my step function down here. I've got to copy my values from the SBML dictionary to the cell dictionary. So I create cell.dict of quote, I could use the same name, D equals, and again, I realize this looks like it should be automatic, but the tracking fields will recognize the cell lattice. They don't recognize the SBML lattice. If I don't remember how to reference the cell dictionary, go to CC3D Python, cell attributes, and I should have somewhere access modify, the very first one, access modified dictionary attribute. And that will paste in the syntax that I need to do that. I don't remember that it's there. And cell SBMLDN, I should have them. Right. And I'll give people time because this is actually the full model. Try to figure it out on your own based on what you saw, and then I'll show you the code in a second. In player, you might want to create a second visualization window. And notice under cell field, I can select notch and select delta. I can lay this out using tile. And now I can visualize delta notch as we go forward. This is that additional randomization that I've done. And now, oh, we crashed. Interesting. All right. Everybody else has been complaining about Data Hub crashing, and I haven't had a crash. So it was my first crash. How do we get the perimeter of a cell? The neighbor iterator gives you the contact areas, and you sum the contact areas just the way you sum the number of neighbors. So you create a placeholder.
Right. Is it just like we have cell dot volume? Do we not have something like cell dot perimeter or cell dot surface area?
You would have that if you had turned on the surface area constraint, but we didn't.
Okay, okay, got it. Thank you.
But that's a good question. If you turned on surface area constraint, made it lambda equals 0, so it doesn't do anything, it would then you would have it excessive.
Yeah, that makes sense. Thank you.
An error message, but I try to run error in model string, syntax, unexpected slash. Remember my debugging advice. If you're getting an unexpected slash, it means that you have an unmatched parenthesis in your antimony string. TJ says it's cell.surface. And actually, maybe in current CompuCell, cell.surface exists even if you don't use the surface constraint. It may be defined always. You could try it and find out. What is the line in the loop for self.get cell neighbor? Use the Twedit function to paste in the visit cell neighbors. I'll show that in a second. Okay. Let me see if I can reload where I was. I may have lost my simulation, in which case it'll be too bad. Okay, so the question was, looks like I lost everything, huh? Which one was it? CC3D project. I guess I opened the wrong one. I certainly don't want to have to redo all of that in front of you. Let's see, what's this one? I'll go to my final. All right. So the first question was iterating over neighbors. Iterating over neighbors, you don't need to use the parentheses here. For neighbor, comma, common surface area and self.get cell neighbor data list is the syntax. Show you that again here. And let's see if this runs. I'm going to create a second visualization field. I'm going to visualize notch. I'm going to visualize delta. I'm going to tile. And now I'm going to run it. And this is already equilibrated pretty well. So I'm going to stop that, start it over. I have to joggle my screen. Notch, delta, step, randomize it a little bit. And now I watch them develop. And you can see it takes a while for the pattern to form. You see the delta, high delta cells are isolated. And the notch surround them in loops. See where people are. And I realize that this is a model that takes some time to do, but this, if you can do the steps in this model, you can build essentially any model with connected multicellular networks. The one thing that we didn't do was connect it to secretion and absorption. My cells are all turning the same color. Did you randomize your initial conditions? It may take a while. If you don't, it can take a bit of time sometimes for the pattern to show up. You notice I'm already at Monte Carlo step 3000. So let's see other questions. So that surface, yeah, that's what I thought. If you don't load the surface constraint, it doesn't calculate. So is anybody else having a problem with this not running or doing something strange? Why don't I get a show of hands by people who have it looking something like what I have here? If the cells are all turning the same color, one possibility is that when you copied the cell dictionary entry, you didn't do it inside the cell loop so that all of the cells are getting the same number assigned to their dictionary entry. So I would check that this pair of lines is implemented correctly. Anybody else having problems?
When I played around with changing the dictionary key in the initializing statement as well, they started going all the same color.
So which value did you change?
Go up. So it's in the init.
In the init, in here, in the start function, or when you define the model?
Where did I? Oh, actually, no. don't worry. I don't think that was the problem.
It's a reasonably sophisticated model to try to write in half an hour. So it's I understand if they're glitches. And we've seen all of the things we're doing here pretty much, but we haven't had a lot of time to practice. That's why I wanted to walk through it with them. It's like anything else. The first time you do it, it's painful, and as you repeat it, it gets easier. At some point, fortunately, because of syntax errors, it never gets so easy that you think that it's trivial. Because as you see, I do this a lot, but I still will make typos, make some mistakes. Which is why I keep going back and forth. As practice of developing models, I try to develop models so that they all work step by step. You don't have to finish it before you can do it. And so I try to do it in blocks so I can do them, debug things one block at a time. And I also will always keep going back and running it to check that I haven't made a syntax error. Because it's easy to catch them when you've just done them. After later on, it's harder.
Okay, I found where it is. That was, if I change my dictionary keys to delta and notch instead of D and N, it will make them all the same color.
So you mean if you call this here delta?
Yeah.
Okay.
Yeah. So that might be maybe why people are having them going the same
Well,
color.
so if you call it delta here, then when you created your tracking field, you would have to call it delta. This attribute name has to match the dictionary entry. If I call this delta here, it shouldn't change it. Check. Let's see. I call it delta there. Now let's see. I called it delta here. And let's see if that works.
Oh yeah,
So
sweet.
it's-
I was matching the field name, not the attribute name, so that's
Right.
probably why.
So that was the question of somebody. Who was it? Somebody very helpfully said it's dangerous to reuse names because you can make mistakes like that. So trying to see who said that. It was Daniel made that said that was a risky thing to do because it was liable to cause mistakes. And so Daniel, you were 100% right that using different names is a safer thing to do. Notice here the pattern's taking a while. You have all these yellow cells that aren't able to decide what to do. One of the interesting things here is as you change the pattern, you'll get evolving. This is called frustration. The number of cells is such that you can't get a perfect checkerboard. And so these yellow cells are getting undecided about which way to go. And that happens biologically as well.
Was that line of code there, is that initializing the dictionary entry?
Here in this line, cell.dict quote D equals.
No, in the track cell level scalar attribute.
Yes.
Okay, that's the initialization.
Yes, that's right.
Okay, sweet.
That creates the count. That creates the field, but it doesn't actually create the dictionary entry. You have to create the dictionary entry here in these lines. Sorry, here is where you're creating the dictionary entries. 48 and 49.
Okay, so we don't have to initialize it before the step function, like before we want to use it.
Right. It will display essentially nothing until you've given those values.
Okay, sweet.
And the reason for that is that for example, medium doesn't have, if you don't have a dictionary entry for a medium, it shows a 0 value. So the default is that if the dictionary entry is missing, It doesn't crash. It shows 0.
Okay, awesome.
Other questions? Oh, you've got it working? Great. Anybody else having issues? I think this is really, it's great progress. Let's see, this question. Why is delta always surrounded by notch? Can it happen the other way around? That's a very good question. To dig in that one, that's a really biological question. It has to do with the specific pattern of feedback that we've used. You'll notice that if we go back, it's maybe not so obvious here. Notch is controlled only by the neighbors. Delta is controlled by notch inside my own cell. And so the pattern of inhibition is different. Notch is turned on by notch in delta in neighboring cells. Delta is inhibited by notch in my own cell. And so there is an asymmetry there. And again, I would recommend talking to Lorenzo, who's an expert on delta notch patterning, because there are an incredible number of subtleties. It's a rather complex set of chemical pathways, and simplifying it into just 2 species. In reality, you have delta on the membrane, delta a notch on the membrane. You have notch intracellular domain after cleavage. The signaling actually reduces the amount of notch on the membrane. So there are a whole series of complex steps that occur during delta notch signaling. This is a caricature model, but it does have the basic idea that you have a delta activating notch in the neighbor, notch inhibiting delta in its own cell. And those are the 2 and then the contact. Those are the fundamental ideas. So definitely, if you were going to be doing research, you wouldn't use this particular model. You'd use something more sophisticated. But fundamentally, the results would be very similar, and I'd have you typing 30 lines of antimony instead of 2. So the goal here was to get the idea across in a biologically meaningful way without too much typing. Other questions? I think these are great points that people are bringing up. Uri Alon has done some beautiful modeling of delta notch and experiments as well. Can we have biochemical gradients within the cells? So in this case, when we're using network models, we're specifically assuming that we can treat the concentrations as uniform within the cell. Giulio on Friday will show you how to do spatially distributed chemical concentrations within cells that have explicit representations for things like contact signaling and planar polarity. He's going to do the Drosophila planar polarity model. You can also use chemical fields and diffusion, and you can write reaction diffusion equations. But the complexity of the reaction diffusion equations we can write is somewhat limited. Solving reaction diffusion equations is quite expensive computationally. And so if you can get away using scalar values inside cells, saying that the cell has a notch level, as opposed to getting the value of notch everywhere within the cell, things will run hundreds or thousands of times faster. But of course, if you have spatial gradients, for example, of calcium, then you need to put those in. And so the question is fundamentally not, can you do biochemical gradients? You can, but whether, and Gilberto will show you how to do chemical gradients for leading edge formation. But the key question is never, can you do it? The answer is you can always do it. The question is, you know enough to specify the model in a meaningful way, if it's that complex, 1. And 2, if you try to solve it that way, is the extra computer time make the model impractical because it would take a lifetime to run? Or if it's slow but practical, is the extra computer time worth it, given the amount of extra explanatory value of the model? Can we have a model where the expression in each cell starts differently, but later they're coupled to have the same expression? Well, one thing you could certainly do is you could, and this would be a good extension, if you liked, you could have the D average here depend on a parameter that changed in time. So the D average signal was 0 to begin with, and then you had a control on that that changed in time. And that's pretty well what we do, for example, in differentiation models of semitogenesis, where there's a gradient of a morphogen like FGF8 or retinoic acid, and that external gradient controls the strength of response between the cells or the strength of the delta notch coupling between the cells. So yes, one can definitely implement that. As I said, the one thing we didn't do was do chemical absorption from a chemical field and couple it to an intracellular concentration. If we did it, it would look very much like this. We do uptake total count, which you saw yesterday, and then you'd say something like cell.SBMLDN D average equals uptake total count, That would be for uptake of something. And similarly, we could do secretion, where we say secretor of, and then a value coming from our SBML, our antimony model. The thing we'd have to do there, though, is we'd have to subtract the mass out of the antimony model by hand and hand it over to the secretor. It wouldn't do the subtraction automatically. On uptake, it'll do the subtraction automatically, not on the absorption. For example, for a paracrine signal. Yes. Another case where that would happen would be infection. If I have a viral field, viral density field, and my cells have a receptor, a viral receptor on their surface, I want to model the internalization of the virus. That would be an example of that too. We did that we did that actually yesterday in the avascular tumor spheroid. The cells take oxygen up, they use oxygen or glucose, whatever that field represents, and turn it into mass. In that case, we didn't have an SBML model for the growth, but we could have put that into an SBML model to control the growth rate. Okay. Other questions? All right. Well, I think that was it was a lot of work, but I hope that was a learning experience for people. So this is what we saw. And it's worth, why don't we just take a minute, just a minute. There are a lot of things you can do with this model. One of the things we could do with this model that actually is quite easy and is not as sort of fun is just see what happens if we made our cells smaller. So if we wanted to make our cells smaller, all we would have to do is go to the beginning of the simulation and say, instead of width 7, let's do width 4. Then we'll have more cells. Why doesn't everybody try that and see what happens? I always like to do stop and then hit step, single step. And again, if it doesn't draw properly, click the bottom corner to redraw. I think the other great thing in CompuCell besides tracking fields is this tile function. And one of my big regrets is that Macs don't allow tiling of windows. That's a fundamental problem with the Macs. Windows, Linux are okay. So let's run this. You see I have more cells. It's going to take a little bit longer for the pattern to establish itself now. There's a first high delta surrounded by notch, and it's going to pattern off of that. You'll see the pattern spread, the checkerboard develop as a wave. You could also do this where the strength of the delta notch signal is different in different cells, and that was what I was going to do next. Another thing that you could do is these cells fill the whole space. What if I went back and it had some medium? So I had some free surface on my cell. So I'll make box min 10, box max 32, Y min 10, Y max 32. I'll put my size back to 7. Now I'm going to have a gap around the cells. Let's see what happens then. Notice the patterning is a little bit different on the free surfaces because there's no delta notch signaling on the surfaces. You can't get that salt and pepper high delta surrounded by notch if you only have one cell. That would be something to do. Why don't people try just generating a single cell? See what happens. The answer is not much, actually, but you can try that out. Okay. So there's a lot you can play with this very simple model. Okay. I'd like, we don't have too much time. I don't want to run over too much because I know we need to get to we started about 10 minutes late, but I don't want to take too much more of your time, especially because we've got the guest lectures this afternoon that should be really good. And we need to do our hackathon preparation. But I did want to show you one other fundamental thing. And then the whole second half of this lecture, you'll have as a homework exercise. I'll just show you what it is, and then you can play it. I want to talk about steering panels. We know that things that are specified in the XML, like contact entities, I can change while the simulation is running. And there's some new features that allow me to connect XML variables to Python in new ways. Those are not, I don't think, implemented in the version of CompuCell up on NanoHub yet, though. But one of the things that we might want to do, especially if we're going to be distributing this model as for other people to use, as opposed to just research, is to have a user be able to change values while the simulation is running. And to do that, we use what are called steering panels. And CompuCell allows you to pop up a window that allows you to change variables as the simulation is running. And I want to go over this for a few minutes because it uses some programming concepts that we haven't talked about yet that are pretty important. It's what's called event-driven programming. In this case, when a person changes a value in a steering panel, you need to do an update, but that event may never happen. And so what you have to do is create functions first to generate the steering panel, and then that watch for changes in the steering panel settings and update variables when those changes are made. So what we're going to do is we're going to create a steering panel window and define the parameters or variables we're going to modify in it. We're going to define a function that watches for the panel updates and reports them. And then once those are reported, we have to change the parameters that are at issue. And I'll go over the syntax first, and then we'll do it together. So there are two kinds of steering panels menu options. And again, as usual, Twedit has all of this. And the question is, where do you put it? And it's going to be like the tracking fields. These things go between the init, after the steppable, and before the start function. So there's a sort of a pattern of things that go in that position in the code. And if I sit here and I go to CC3D Python, there'll be an option that says steering panel, and I'll see three things. Set up steering panel, check if steering panel is updated, and get updated value of steering parameter. If I set up the steering panel, I get a whole bunch of stuff, really a whole bunch of stuff. And for the moment, I don't want you looking at all of that stuff. We'll go back and edit that stuff in a minute. There are, in fact, many kinds of widgets that could be generated. CompuCell only supports two of them. It supports what are called sliders, which adjust values continuously, and it supports lists where you have a pull-down menu that you have options for. I'm just going to show you the sliders for today. The lists function almost the same way, and they can be quite useful in their own right. To create a steering panel, we have a function, def add steering panel, that takes as an argument self. And then there is a function inside of it that says add steering parameter, the name of the variable, that's going to be how it's labeled, its default value, its minimum and maximum value, how many decimal digits we're going to display, and then the fact that it's a slider. And we're going to be controlling two parameters in our delta notch model. We're going to be controlling the variable A here and the value B. You notice A is 0.01 and B is 100. So they've got different scales. We're going to add those. Okay. Once we've added the steering panel, we have to create another function, and that also goes in the same location between the steppable and the start function. And this is what processes changes. And this is a function called process steering panel data. A equals self.get steering parameter, B equals self.get steering parameter. Notice that these are inside of a function definition, and so they're not available outside of that function definition unless I do something. I can store them in a dictionary, I can define them as globals. I have to have something way of getting that information out of that function. One thing that you can do, mainly for people to use this as a if you're using this as a, for example, teaching tool, is you might want the simulation not to start immediately, but have the person select some options and then start the simulation. Run option 1, run option 2, run option 3. You can create an endless, a futile loop using a steering panel, say of a pull-down type, in the step function, while self.get steering panel simulation type equals select simulation to run, pass. That will just keep waiting until the user pulls down the simulation type button and changes it to something else. And so that's a way to have a delay for user input, because so far we haven't really had ways of users to interact dynamically with the simulation. So that's something that you might want to do. So let's add a steering panel to delta notch. We have our model here, and what we're going to do is change the values of A and B, and we'll see what happens. Somebody said, what other things could happen? Could you get reversal of the pattern, for example? This is something we could investigate. We could steer any of these parameters. We could steer H, we could steer V, we could steer K, but we're going to steer A and B. And the completed exercise is 4.1.2 delta notch steering. Okay, so the assignment is using the code from the previous exercise, which you have up on your screens. Remember, let's add a steering panel. And this is what we're going to add. And you can either add it by typing this, which is rather tedious, or you can paste in the add steering panel functions from a Twedit. And I'll warn you again that Twedit is going to give you lots of options to illustrate your possibilities, and you're not going to want to use all of them. For example, if I look at what Twedit has just pasted in, it's added 2 steering panel items, one of which is a slider, which I want, and one of which is that box combo list that I don't want. So the first thing I would have to do here is get rid of the second option, which I don't want, copy my first one, and now what do I have to do? My parameter is the variable name that I'm going to display. And here I'm just going to keep the variable names as A and B. The next thing I have to do is define the default value. And my default value for A was 0.1. My default value for B was 100. And I have to say what range of values I'm going to allow the user to type, because I might have values that cause my program to crash, so I don't want them to be able to give those. So here I'm going to say that the minimum value here is for A is 0, and the maximum value is 0.2. 0.02. Now you could say, how do I know that? Well, I played with the simulation and I know. Usually you add sliders once you know what you're trying to do. It's for publication purposes rather than for research purposes. This is really a presentation option. Min value here, 0 again. Max value 200. And if I have things that are that big, I better have 3 decimal digits. Can make the other one. Sorry, decimal digits here, sorry, 3. And the other one, I'm exactly backwards. I'm integers, so I have 0 decimal. Okay. So people can try doing that. And then we have to update our values of A and B, and that goes in this processing steering panel. And there's going to be a bunch of stuff here that we're not going to need. This is informational printouts that we don't need. We're going to have the combo box one that we don't need. And we're going to keep the value get steering parameter. So we need to know what the value is going to be. Here it's going to be A, parameter value of A. I hope people are following along with this. B, get steering parameter B. And then the next thing I have to do is update the values in my cells. And so I'm going to have to iterate over my cells. And I have to remember to add the dictionary entry if I don't remember my syntax. SPML solver. Get SPML value in a specific cell. My model name was DN. My variable name was A. As Daniel pointed out, maybe we shouldn't be using A twice, but here it is, A. And I can copy that. and make it B. Get rid of the extra lines. Okay, try that. Let's see whether people can do that, get that to work. And if you want an extension, you've got that going already. You could try steering other parameters, or you could also not have every cell get the same value of A and B. You could put in a little bit of a random perturbation on A and B when you update. That makes it a little more interesting. I'll leave the code up here. I'm going to see whether it worked. It worked. Notice I have a new window here, steering window. I'm going to do my tile function. Let me do a step. Oop. Tile again. Step. And now I can click in here and I can change my value of A. Change my value of B. And see what happens. I can keep changing them. I better be displaying delta or notch. Displaying the cell value isn't very interesting. I could say, well, what happens if I change A? It's changing. This particular output isn't that exciting. You'll find that if you push the values of A and B too far, you lose your pattern. And you can actually get some reversal of the checker. Is that working for people? Let's try them. This has the advantage that if I want to explore things, I don't have to go edit, save, and rerun. I can do it live. The disadvantage, of course, is unless I have some way of saving my values of A and B, I don't remember what I did. I have to write them down, or I have to output them to a file. It looks like some people gave up. I'm sorry if that was discouraging for you. I hope you'll be able to go back and look it over again. But I think this is an important functionality in CompuCell that I wanted people to see. I'll let people keep playing with that. I'll leave the code up here. I'm not going to be able to go through all of the things that I had planned today, but that's fine. The basic things are here. I just want to allude to a few things that I was hoping to talk about. One of them, and so here's the results, and you can load the file to 4.1.2 delta notch steering. Okay. Something that was asked about the other day that I think is important that we didn't talk about is somebody said, well, what happens if I forget to put something into my code? And I did that already. You saw that today when in the XML, I had forgotten to put in the neighbor tracker. And I went into my XML and I went here, I went to CC3D ML and added a plugin. And so Twedit is quite smart. If you have an existing plugin and you want to replace it or edit it, for example, I do contact energy. It will ask me whether I want to keep the old value and comment it out or replace it. So for example, if I added more cell types and I had to do a new contact energy hierarchy, it'll keep the values you had from your old one and then give you the opportunity to add more. Actually, Twedit's pretty smart about updating that. On the other hand, if you have Python issues, for example, suppose you didn't have cell division, you didn't have mitosis, you forgot to put mitosis in, and now you want to add mitosis. You say, what do I do? Don't panic. It's possible to add additional steppables. And so here you go, and this is a little bit hidden. It's not as well documented as it could be. It's a very powerful function. You select your steppable file here in the left-hand window. I hover over that, I right-click, and you'll see a bunch of options. Open in editor properties, convert XML to Python, I click Add Steppable. And now it'll give me an option box where I can give the name of the steppable. That's any name I like. Don't put in spaces, don't put in special characters. How frequently I want it to be executed, every Monte Carlo step, every 10 Monte Carlo steps, or so on. And what kind of steppable I want. A generic steppable, mitosis steppable. AJ had asked specifically about cluster mitosis. There's a special steppable to divide cluster cells. Or an initializer run before MCS secretion step. The ones that you'll typically use the most would be generic and mitosis, cluster mitosis if you have compartmental cells. And you can add those extra fields at this time too, or you can do it the way we've been doing it for tracking. And if I click OK, I need a name, mitosis. I click OK. What did it do? It created class mitosis steppable, pasted in all the standard boilerplate that I'd get if I used the Twedit wizard. And the key thing that it's done is if I go into the main Python file here, which is something we almost never look at, you'll see that it has created a new steppable here. CompuCell setup register steppable, steppable equals mitosis steppable frequency equals 1. And so that's handled automatically. So if you want to add a steppable, you can do it essentially with a single click. And that's a very powerful functionality. If you want to get rid of it, you have to do it by hand. You have to delete the steppable there. You have to go in here and delete that line where you register the step. So that's a functionality that I think would be interesting. If we had more time, I would ask you to couple delta notch patterning with growth. And I'm going to just allude to a few exercises that you could do now as homeworks and show you a few results before we wrap up. Notch can act as a promoter of growth. So what we could do is we could start with 1 or 2 cells, have the cells grow slowly at a constant rate and divide at a constant doubling value, and ask what does the delta notch pattern does. In this case, we're asking a question what the growth does to notch and delta, not the other way around. That's an exercise that you have available. The more interesting thing is now have the growth rate be proportional to the square of the notch level. And so now cells with high notch grow, cells with low notch don't grow. And you can run that. Since a lot of cells have high notch, that's not so interesting. But remember, only a few cells had high delta. They're surrounded by notch cells. And so that's a more interesting one, because if you have two delta cells next to each other, they'll turn off, one of them will turn off. And that's actually a way of maintaining stem cell niches. High delta corresponds to stem-like, and those stay isolated. So you can do a situation which the growth rate depends on the delta value, and you can get some quite interesting patterns of growth in those two cases. So I think that's an exercise people should try as a homework problem. You can try different spatial patterns, different levels of membrane fluctuations. Delta notch is a source of real sort of critical biochemical mechanism, and there's a lot to do. The other exercise, which we're not going to have time to do, which actually stayed up all night writing up for you, didn't go to bed last night because I wanted you to have this, but that's life, because somebody asked about calcium signaling. And TJ and I have worked on using a model that was published by Jeremiah Zartman of Notre Dame, looking at cross calcium waves in Drosophila imaginal discs for wings. And in this case, you have an internal oscillator, and there's a coupling of calcium through gap junctions and also IP3. There is a pre-existing mathematical model that was developed for the oscillations. I'm not going to go through the detail, but it has a particular control parameter, a VPLC, which is the rate of production of PLC in the system. And when you run that model, you discover that if the rate of production is high, you get spontaneous calcium oscillations. And if the rate of production is low, you get a static steady state. You can investigate as a function of the VPLC level, whether you have oscillations or not, and how big they are, and what their frequency is. And you can then put those inside of cells. Initially, we build the cells that don't do anything. Then we add that calcium model to the cells without coupling. Some of them in oscillatory state, some not. And they oscillate or they don't. Nothing very interesting happens. And then we couple through gap junctions the values of calcium in neighboring cells and the values of IP3 in neighboring cells. And we do that essentially the same way we did this for the delta notch. We iterate over neighbors, we calculate the flux, and we pass the values to our ODEs. And when we do that, we see that we're going to get calcium waves. And I guess I can run that simulation even if we're not going to walk through it, just because it is really pretty to watch. So let's look at that together. This is basically a simple generalization of the delta notch signal that we did. Oops, I didn't load them. And here I have calcium and I have IP3. I'm going to visualize. And I'll let that run. And it's going to take a minute.
While that runs, Daniel had a question. He says, I saw the bifurcation diagram. Can that be done in CC3D?
So if you're going to do bifurcation analysis, I would recommend taking your antimony models and putting them into the Jupyter Notebook, because you're going to it's easier to do parameter scans in Jupyter Notebook. But yes, you can do bifurcation analysis inside of CompuCell. It's just going to run a little bit slower because you're going to be using all of the machinery of you're not using all the machinery of CompuCell that's going to be taking time to run. But you can do parameter scans and plot the results. Just the way we plotted a time series for a simple ODE model inside of CompuCell using that program that we gave you to begin with, that tellurium V3. You can build a very simple bifurcation analysis tool based on that. So anything that you could do in Jupyter Notebook, you can do here. You load the same NumPy functions and use those. If you really want to do fancy bifurcation analysis, the best tool is still XPP-Op. This is Bart Ehrmantraut's XPP-Op. That's a 35-year-old program. Nobody's ever done as well. It's a beautiful tool. And so if you've got two coupled ODEs or 3 coupled ODEs, you want to do bifurcation analysis, better type it into XPP-Op and run it there. But you can certainly do it here too. Okay. This is running a little bit slow. I'll let it run while we talk because I want to wrap up. I'm running a little bit late here. But you're going to see if NanoHub ever gets to it, that around step 1000, you're going to get calcium waves. It's sort of blink and you miss it because it's static for a long time. The calcium waves go through very quickly, and then it's static for a long time, and the calcium waves go through very quickly. So keep an eye out here. The thing that's a lot of fun that you can do with this model, and again, this is available to you, is one of the things that calcium release does, and we saw this in the example that was given yesterday as a proposed topic, is that calcium release from the endoplasmic reticulum can cause actin-myosin contraction. And if you're in epithelium, like an imaginal disc, you get contraction of the apical ring and the actin cortex. You get apical contraction. In reality, the volume of the cell doesn't change. The cell becomes more columnar. But looking from the top, it looks like the cell shrinks. And so in a 2D model, you change the target volume of the cell to shrink to correspond to that apical contraction. And then you have the cell relax when the value of the calcium goes down. And so you write a little simulation where the volume of the target volume of the cell changes with the calcium level. In that case, you'll see mechanical waves propagating through the cell, the tissue, as well as chemical waves. And what's really interesting, of course, is that usually those mechanical waves have feedback back to the chemical waves. I didn't get that far with the model, but one could add that. And so somebody had asked specifically about seeing calcium waves. And so I stayed up all night to try to show you those. TJ had done the majority of this before for something else. And then I decided I was going to recode it all from scratch. So that gives you some idea of how long it takes. It took me, actually writing it up took more time than doing the coding. The coding probably took me about 2.5 hours, and writing the slide deck took me another 3 hours. That's what I did between the time we broke last night from our meeting and today. Ah, there you go. There's your calcium wave coming through. Does everybody see that? One limitation, unfortunately, with CompuCell on NanoHub is that you can't save movies. And that's something we hope to fix in newer releases of CompuCell. But at the moment, you can't save movies. If you're running CompuCell desktop and you go under, I'll let that wave go through before I do it. And you go under Tools and Configuration, you'll see under Output that I can do update screen every so on. I can do save image every nth Monte Carlo step, save visualization snapshots every nth Monte Carlo step. CompuCell has actually got very powerful tools for saving movies. You can save any individual set of screens, any different renderings of the same thing. If you have 3D renderings, you can save those. And there's a lot of power in how you can save both images, rendered images, and raw data for post-processing. But it does not, that's not activated on the Nano. So if you're running desktop, that would be good to show So people who are running desktop or a cluster and doing the hackathon, we could get somebody to teach you how to do movies if you like. But I did want to show you this and just show you the end. Here's this kind of same patterning with a little bit of mechanical contraction. Here's the kind of thing you get if you have large scale mechanical contraction. That kind of coupled mechanical contraction shows up. This kind of extreme mechanical contraction is usually deleterious. You don't want disorganized contraction in an organism. But it is used in a whole variety of things. Of course, the heart has essentially that kind of behavior. There's a beautiful simple organism, multicellular organism called Triplax that actually crawls by doing that kind of calcium graded contraction. And that's a simulation one can use this to do. And so that's really, I know we skipped a lot of things, but I hope you get an idea of what you can do from this. You could take that model that I uploaded and sent around, and you could ask a bunch of questions about how the parameters affect the wavelength, the wave frequency, the strength of the waves. How does the tissue morphology affect the wave propagation? Do you get single waves or spiral wave chaos? If you have variability in parameters, do the waves get interrupted? How much robustness is there in the system? What do you have to do to make the models of intracellular transport more accurate? And so those really were the things that I had hoped to talk about today. And I'm going to launch again a module poll. Please let me know how things went for you. And I'll give people a couple of minutes, 4 minutes to do the module poll, and then we'll turn things over to Hayden. If there are any other questions, please let me know. So let's see here. At some stage, it'll be helpful to go over making movies. Getting resolution right is tricky. That's true. And I definitely hope that somebody will be able to do that. We didn't include it in our main lectures because we don't have the movie functionality in the NanoHub. And it didn't seem fair to spend a lot of time showing a functionality that's only available to some people. Louise says the calcium model is useful for podocytes. Great. Hope that will work for people.
I did want to say we have been talking recently about putting together a tutorial online on how to make movies in CompuCell, so we'll make sure that everybody who did attend the workshop is included on that when that goes out, in case we don't have time to cover it in the next 2 days.
Okay. Now you've got a nice wave propagating. One thing with NanoHub is the amount of computer time you get is highly variable on how many users there are. And so the rate at which the simulation steps through will change as time goes on. If you're all running it, I do encourage you to run this simulation. It's really pretty. And the one with the mechanical instability, I think, is a lot of fun. It's a lot you can do with that. It's a great framework that you could build on. And again, this is a model that's built on top of the methods we developed with Delta Notch. I would have loved to walk you through building it, but fundamentally the steps would have been identical. The ODEs that we loaded would have been a little bit different. The coupling would have been just a little bit more complicated, but essentially it's doing exactly the steps we did for Delta Notch, just with a little bit more detail in each step. Okay, if people could fill out the questionnaire, we'd be most grateful. I'll give people another 2 minutes to fill out the questionnaire. I realize being asked to fill out the same questionnaire 25 times gets tedious, but we do take it very seriously. At the end of the day, we look over all these questionnaires, all the typed comments, and we adjust the lectures for the next day based on them. Each instructor gets your feedback. We do the slide decks. We really do take these questionnaires seriously. I realize that we're not perfect lecturers, we're human, but we do try to adjust everything that we do to the needs of the community. One more minute on the questionnaire. Anything else about delta notch and signaling connections? I realized trying to do all of that in what we had 4.5 hours to cover all of it. We could spend a whole week just doing integration of SPML and multi-cell modeling. In fact, Herbert takes a whole week just doing just doing the antimony model. So to try to get all of that week's worth of material into 1.5 hours is challenging. But I think the great thing about antimony is it's simple. The models you can build are very, very complex, but the programming is very simple. That's why I like it more than something like Copazi. Copazi is a very, very powerful tool for analyzing networks, but the learning curve is steep. Antimony, you have to know 5 commands and you're done.